So how you get that decimal point of the mass is related to the percent abundance of those isotopes, meaning the percent abundance is how much that occurs in nature, the natural abundances. So you can see hydrogen 1, 99% of hydrogen is hydrogen 1. Less than a percent is deuterium, which is hydrogen 2, and even a smaller amount is tritium. But because they do exist, they throw out the atomic mass number to the average atomic mass number of 1.008. It's because there's this relative abundance, the percentages will cause the mass to be in a decimal. So isotopes are really the weighted average of all the different masses and the percent that they occur. That's how you get that decimal place. So helium, there is a helium-3, but basically almost 100% of helium is helium-4 with a mass of 4. But because there's just a little bit of it, that throws off the atomic mass of helium to have a decimal point. Back up to lithium, 92% have a mass of 7, 7.8%, or about 8% will have a mass of 6. But because so much more have a mass of 7, the atomic mass on the periodic table is closer to 7. So here are just some of the relative abundances. Again, it all depends on the mass is always going to be closest to the one that has the most percent abundance. So the atomic mass unit of an element, the AMU, atomic mass unit, is a weighted average mass of the atoms. So that weighted average mass reflects both the mass and the relative abundance, how much it occurs in nature. So let's look at an example of calculating atomic mass from isotopes, but let's use the example of this chipmunk. And I never really saw chipmunks before coming to Michigan, and I think they're actually pretty cute. We'd have squirrels back there, and those squirrels in California are pretty cute. The ones here in Michigan, boy, they're vicious. They're these big scraggly things that, and sometimes they don't even let you enter your house. They just stand in my walkway and just stare me down. So I just end up running away from them, and they'll come up to my window and stare at me and intimidate me. Anyway, so if we were to look at these little chipmunks, we have a little one and a medium-sized chipmunk and a large chipmunk. And these are actual sizes of the ranges of chipmunks from 46 grams to all the way up to 125 grams about. So looking at relative abundances, this says that 15% of the chipmunks out there have a mass of 46.6 grams. Now I just made this up. So as far as the relative abundances, just for this purpose, I don't know the abundances, but I think most of them are weigh about 103.7 grams. But don't take it that these are the actual relative abundances. Then here, 80% have a mass of 103.7. 5% have a mass of 124.52. So I would assume that if we're going to calculate the actual mass, the atomic mass, we can say that it's going to be closer to 103.7. So how do we do this? Well, we have to take the relative abundance and change it into a decimal. So this is going to be 0.15. This is going to be 0.80. And this will be 0.05. Let's make atomic symbols for these. This is like the chipmunk small. This is going to be the chipmunk medium, and this is the chipmunk large. So then what we're going to do, we're going to take each of these and we're going to multiply the abundance times the mass. So we're going to have the mass of the small one. We're going to multiply it by the abundance. So we're going to take the mass of the medium one and multiply it by the abundance. And we'll take the mass of the big one and multiply it by the abundance. What we did is we multiplied that out, and for the first one we got 6.99. For the second one we got 82.96, and for the third one we got 62.26. Then what we do, we add them up, and we're going to get 96.176 grams. So this will basically be what most of them, this is like if I were to look this data up, and again I'm just making this up as far as the relative abundance, I could say chipmunks have a weight of 96.176 grams. So let's try one with an actual atomic number. Again, I'm going to use this made up one Z, but it has to do with atoms now. Element Z has three natural isotopes. The isotope with a mass of 33.005, Z33. So notice this corresponds to the mass, this corresponds to this mass, this corresponds to this mass. So these are the relative abundances. 65% have a mass of 33, 20% has a mass of 34, and 14 has a mass of 32. I can guess that it's going to be closest to 33 because most of the isotopes, 65%, have a mass of 33. What I'm going to do is I'm going to take that and put it into a decimal. So that's going to be 0.6512. This will be 0.205. This will be 0.1438. And I multiply this number times the atomic mass. So for Z33, I multiply 33.005 times 0.6512. For Z34, I'm going to multiply 34.133 times 0.205. And for Z32, I'm going to multiply 32.30 times 0.1438. So we write this all out. The atomic mass units multiplied by the abundance equals 21.49 in this case. 34.133 times 0.205. We get this amount. And then we multiply this atomic mass times the abundance, and we get this. Then we just add these all up, and we get 33.131 atomic mass units. So that's the atomic mass of this fictitious element. That's what the atomic mass here is, the one that would be on the periodic table, and that makes sense because it's closest, 33.13 is closest to this one, which had the most relative, or the highest relative abundance.